Our first speaker is Dr. Mark Mills. Mark is an environmental engineer at the US EPA Office of Research and Development and is a principal investigator for projects characterizing the occurrence, transport, and fate of contaminants of emerging concern, or CECs, and legacy contaminants in the environment and the management of contaminated sediments. Dr. Mills leads research to identify sources of contaminants to aquatic systems and tracing their movement through the environment and the food web. He also leads the development of analytical methods for CECs, such as PFAS, endocrine disruptor chemicals, pharmaceuticals, and personal care products, and stable isotope chemistry for environmental samples in water, wastewater, soils, and tissues at the National Risk Management and Research Laboratory for US EPA. These methods are used to characterize potential sources of CECs and legacy contaminants, their management in water, wastewater treatment, and new technology development. Dr. Mills has a BS in Civil and Environmental Engineering from Texas A&M University and an MS and PhD from the Texas A&M University.
Thank you all for coming. I was asked to cover PFAS sources associated with potential contamination to drinking water. There's a lot of information here that I'm going to have to cover in a very short time, so sit down, buckle your seatbelts, and also note that if I was to do this talk in a month or so, it would probably include more information because it's rapidly evolving. So a quick overview, I'm going to cover some terminology and considerations for the structure of the chemicals, talk a little bit about physical chemical properties. I'll mention some of the production information. I won't get into a lot of detail, talk about potential sources, and a little bit about degradation stability, and then ultimately just touch on some environmental fate and conceptual site models. So a little bit on PFAS as a class of chemicals, just sort of a 101. I'm going to cover really quickly a couple slides for those that aren't familiar. As of the last count, there's thousands of PFAS in production for industrial and consumer products. They are both polyfluorinated, meaning that they have many fluorines, and then there are perfluorinated, meaning they're fully fluorinated. This is also a relatively fast evolving industry. Is very good at making this types of compounds and are generating new chemistries routinely as they explore different functional groups and different halogen groups in order to be able to come up with different performance characteristics and evaluate markets for these are being driven, these changes, and I'll cover this in a minute, are being driven largely by both performance but also the potential for regulatory actions. So a little bit about PFAS. Most PFAS, their intention or their use in industry and consumer products is as a surfactant. They have the rather unique capability of being both hydrophobic and oleophobic at the same time. And that's largely as shown here, which I can't point to, or maybe I can. Can you guys see the pointer? Oh, you can, good. So you've got different functional groups that impart different characteristics to the molecule. Then depending on the use of these particular chemicals, they're going to be aligning themselves at these interfaces depending upon what the intended industrial and consumer use is. Generally, PFAS chemicals have been broken down into what we call long chain chemicals. Those carbon perfluorinated compounds greater than C7 for the carboxylic acids and greater than C6 for the sulfonic acids. These long chains include all the salts and precursors associated with them and can degrade ultimately to these sort of terminal end products, these very stable alkyl acids. These long chain compounds are a concern because they bioaccumulate and tend to have very long half-lives and are thought to be more toxic. The toxicity question is something that EPA and many others are working on, so that is another area that's rapidly changing and will evolve in the next few years. But to give you a sense, these compounds, whoops, now I'm moving things and not even intending to. These compounds include things like PFOA and PFAS, the ones that most of us have probably heard about. Shorter chain compounds, those compounds that are shorter than what was defined as long chain, can still have very similar structural characteristics in the form of alkyl acids. These short chain compounds tend to have shorter half-lives than blood and serum, but they have the potential for being more mobile in the environment. and are not easily removed from some of the common sort of off-the-shelf drinking water technologies that currently exist. An example of some of these might be like the PFAS. To give you another sort of overview of what these structural components are, these are the sulfonic acids. I gotta remember that I got a point over here. Sulfonic acids have this the sulfate group on the end. The carboxylics are carboxylic acid on the end, but there's also an important class of compounds called fluorotelomere alcohols, which are a precursor to some of these compounds. And these result in higher mobility and the potential for volatility as well. As research has evolved, we've determined that there's many other classes of PFAS compounds, and I've included some examples here. I'm not going to go through all of them, but as I mentioned, this is one of the areas that you know, in a month or so or 6 months from now, this slide and some of the following slides would evolve as we discover new compounds that are being developed by industry and implemented in some of the products. A little bit on production. There's primarily two production techniques or production methods: electrochemical fluorination and telomerization. And I'll talk a little bit more in detail on why those are important in a minute. But during their production for their intended products, there are many residuals and other precursors or byproducts that can be formed. So a little bit more on the production. Many PFAS are used both as the end product in a consumer product or industrial application, but there are also many processing aids. An example would be in production of various plastics. You may have releasing agents that are commonly used that can result in residuals or impurities that may end up in the final product, even if it was not necessarily intended to be a fluorinated product. I mentioned industry is changing formulations in response to both regulatory drivers and mounting toxicity and persistence data. This is also a response to certain economic drivers. Industry is always about the next big thing that they can market, and so they're constantly pushing the envelope of what they can do. And as some of these new chemistries come online that may be cheaper, there's obviously an economic incentive for them to move to that as well. However, many of these replacement compounds, we don't have a lot of information on persistence, toxicity, or bioaccumulation. So we're playing catch up a little bit in that sense and trying to understand what these new replacements are as some of these legacies are being phased out. I mentioned some of the production. I'll briefly touch on electrochemical fluorination methods. It's a relatively crude process. It's fairly inexpensive. It does take some expertise to do. There's oftentimes many products that may be off spec and have to be disposed of, but they basically yield branched isomers with a distribution chain length, generally in the carbon length from 2 to 12, but depending on how they manage the process, they can go to higher chain lengths if needed, depending upon the application. An example of that is shown here, is just basically a process to generate these perfluorinated alkanes. It's been around a very long time. As a result of sort of the crude or messy process, you end up with many isomers. I guess I'd stop here for just one moment. It's important to understand that a lot of times industry is producing these compounds with an intended performance characteristic. So it's not necessarily that they're going after the production of PFOA or PFAS. They're going after the production of a technical grade mixture that incorporates PFOA and PFAS and has some of the performance characteristics they're looking for. So generally in ECF, for example, you may have something that's centered around a CA compound, but you're going to have a distribution around that incorporates a lot of other compounds. It's less important to them about what compounds are in there than it is how that mixture performs and whatever the intended use is. So this is an example with ECF that you end up with a broad range of mixtures to include many isomers, and some of the questions associated with that is we don't know much about the partitioning performance, the partitioning, the analytical methods, or toxicity associated with a lot of these isomers. Some of them could be more persistent than others, some of them can be more toxic than others. We don't have a lot of that information right now. In general, the majority of the time we're quantifying them as a group as opposed to individual isomers. If we talk about telomerization, basically this is you have a building block here. You continue. Now I'm not pointing over there. Let me turn on my pointer. All right, now I have a pointer. And then you continue to add this taxogen on, and you can grow that telomer out to different chain lengths. Generally, these will result in straight chain mixtures of carbon lengths, where N is generally only an even number. So it is one of the ways that we can do some forensics or detective work as far as figuring out what particular process, and therefore a little bit about where a potential application may come from, is basically looking at the distribution of the carbon chain lengths as well. And here's an example of one of those, A2F2H, one of the telomere alcohols. A little bit about how these are used. At one point, the dominant production of fluorotelomere industry was about 80% or more of these fluorotelomere products. Oftentimes, this is the functional group that we're most concerned about. They have a linkage to, and a variety of different linkages are available depending on what industry is trying to do with these. But generally, these result in large polymers that have that particular characteristic that we're looking for. However, research has shown that some of these fluorotelomere polymers do degrade. Their half-lives can be very long. In this case, we're talking about several decades to almost 100 years. But what that does mean is that there's a lot of material out in the environment, in commerce, or in final disposal like landfills that may have the potential to break down over time, which means we have a large reservoir of this material that over time could be breaking down and ultimately result in a release and act as a source. I think I already said most of this. I will say that industry has moved away from, through a variety of voluntary actions as well as consent decrees, to move away from some of the longer chain chemistries depending on the application, resulting in more C6 side chain fluorotelomere polymers and other C6 applications. And there's been some additional efforts at potentially modeling what those polymer half-lives are as well. They are showing something very similar as what we were seeing with some of the longer chain. A little bit about the structural impact on fate, and I'll talk a little bit about volatility first. PFAS are commonly manufactured as fully covalently bonded. However, lacking a charge, several of these or many of these compounds can be volatile. These volatile emissions can make it to the environment, and then ultimately through a variety of natural processes can be converted to other forms of metabolites or degradation products that have the potential for being distributed around the globe. This is one of the things that has explained some of the high concentrations observed in some of the food webs in the Arctic, is that it's a combination of food web transport, but also seeing atmospheric transport and deposition into some of these. These have been confirmed by a number of researchers as some of the more volatile compounds that can be produced. And some of these are intended production compounds, so they're trying to produce compounds that meet these certain classifications. But oftentimes these are intermediates or impurities that may be along for the ride that are being released as part of the consumer industrial product. I mentioned several times about industry being very effective at producing these compounds, and there are changing formulations. And one of the ways that we've done a little bit of work to look at that is looking at what's coming into wastewater treatment plants, or more importantly, what's coming out of wastewater treatment plants. And what we are seeing is a shift to the shorter chain compounds. In this particular study, we saw that the majority of the compounds were of the short chain, C5 through C7, with an increasing profile towards those shorter compounds, which is indicative of the shift in production. It corresponds with that. Had we done this a few years prior, we would have seen things centered a little bit more around C8. But we're seeing that industry is responding and coming up with new chemistries as a result of that. All right, precursors. I've mentioned a couple different times impurities, and also I think I've mentioned the word precursors. I did mention that these are broad technical grade mixtures that are out there. So there's a lot of compounds that are either incomplete reaction products, are considered impurities, or considered other sort of degradation products. So it's important to consider precursors, because oftentimes if we simply look at the alkyl acids, we're looking at a very small subset, and I'll give you a slide here in a minute that will make that point as well, but we're looking at a relatively small number of compounds compared to the thousands of compounds that could be there. These precursors are really important because they do degrade in the environment, and they do degrade down to these more persistent alkyl acids. So if we're only taking a look at a very small snapshot of compounds, and we have this natural process that's occurring, or it could be as part of your treatment process, depending on what your treatment systems are that are being implemented, you could be converting these precursor compounds to these more stable end products. resulting in what may even, in some cases, look like an apparent increase in concentration as you move through a treatment system. For example, yeah, it shows up better there than here. Just to give you an example, sort of a mass balance on fluorine. This is looking at a couple of different analytical techniques and sort of what percentage of the compounds that we can analyze for. There's some measurements out there, and I'm not going to get into a lot of detail on the actual analytical side of this, but there's some total fluorine measurement techniques that are out there that are appropriate for solids, like textiles and papers, and that's what this figure is taken from, as a paper that was focused on textiles and paper products. If you can see here, we have a very large, the majority of the fluorine is being detected through this PIGGY method, which is basically looking at fluorine alone. If we start looking at what the majority of the analytical laboratories can look at commercially, you're looking at this LCMS component down here, the small yellow bar. I think it shows up as yellow here. Suffice it to say, it's a very small percentage of the total fluorine that's in the sample. If you move to some of the more researchy kind of methods to look at ionics and volatiles and ultimately to consider precursors, then we're looking at a larger percentage, but you can see still that there's a large percentage of compound or fluorine material, organofluorine material, that we're not detecting with these other analytical methods. Whether this is important or not, that's where some of the research questions are. Some of these could be extremely stable. Some of them may be very non-toxic. We don't have that information yet, but that's part of the research that is needed and will continue to be ongoing. Relative to drinking water, it's also we're probably thinking more about these compounds down here that are being analyzed, just because they're not some of these larger molecular weight compounds that are likely a portion of this unresolved portion. Most likely are not making it through drinking water treatment systems, or maybe even into the source waters in the first place. So maybe these are more relevant in this particular to this particular audience anyways. All right, I mentioned transformation. I'm not going to go through this just out of time here, but suffice it to say that natural oxidation, biodegradation, certain atmospheric reactions can transform some of these compounds to these compounds that we're most worried about. So I've mentioned a couple different things on chemistry and fate, a little bit about sources. I'll touch upon these really briefly because I've only got about 5 or 6 minutes. We're talking about things like primary and secondary manufacturing facilities. So primary facilities being those that are actually generating the chemicals themselves, and then secondary production being those that are using those chemicals in the production of a product. So you might think of the production of the chemical in one hand, and then the secondary production being something like carpet treating or leather and textile or paper treatment, that sort of thing. Consumers use and dispose of these products, so they go down the drain, they go to landfills. Wastewater treatment plants are the end use or the end recipient of some of those things that go down the drain. You've got industrial processes, most notably things like metal plating, some of the electronics industries. Landfills and recycling, again, sort of an end of the life cycle for these compounds, often end up in landfills and now commonly in recycling as well. And then you have sort of direct use in the environment, and the classic example being something like AFFF foams, the firefighting foams, which were by design being put out in the environment in order to fight fires. So those are sort of some of the classic examples. I'll touch upon some of these. It's sensitive. All right, it just goes on its own. All right, so I mentioned landfills and leachates have the potential to migrate, as a result of the leachate, migrate to groundwater, which can be a potential source water. Land where biosolids and other waste are land applied. Pulp and paper mill waste, for example, is land applied. Food waste can be land applied. Those do or potentially have PFAS concentrations depending on what industry sector it's coming out of. I mentioned the direct use, such as AFFF in training and emergency response. Let me see if I can go back and get this other one. Mist and dust suppression for chrome plating is a sort of a known potential source. Where this is important is it can be discharged directly either through air emissions or through disposal of the bath materials. And ultimately, that could end up being a source to the environment. Electronics manufacturing, oil and mine for enhanced recovery, and performance chemicals that are commonly used, such as hydraulic fluids, fuel additives, etc. Food contact surfaces, such as cookware, pizza boxes, fast food wrappers, popcorn bags. Some of that has changed recently. In a very small footnote there at the bottom, PFOA has been phased out. However, that's been replaced by other fluorinated materials, so it's not necessarily a removal of those compounds from that particular usage. Polishes, wax, and paints, stain repellent for carpets, clothing, and upholstered furniture, and then at various times, cleaning products have contained PFAS chemicals. All right. I mentioned that these things are entering the environment through a number of different sources, and really what we're talking about is trying to manage those sources. We use that through typical management techniques such as wastewater treatment plants, landfills, and institutional controls, and ultimately the objective is to reduce or manage the introduction to the environment. I mentioned fate and transport in a number of pieces here. I won't go through a conceptual site model, but this is just to give you a sense. This is from an ITRC fact sheet. They put out a number of very good reference materials that are out there for folks that want to get more familiar with PFAS. But basically, it's to show that as a result of their ubiquitous use, they end up in a lot of different places and therefore have the potential to get into source waters a number of different ways. Some of the common questions that we get as we start dealing with this is what do we measure, how do we measure it, what methods are available, impacts of co-contaminants. Important if you start thinking about some of these things don't occur in a vacuum. It's not just PFAS, it's almost always part of a mixture, and that mixture could be from multiple sources. So you might have a commingled plume coming in from a TCE, you could have hydrocarbon plumes, you could have other things that are interacting with your particular compound, if PFAS is one of them, and we don't have a great sense of what those impacts can be. And ultimately, the objective is to end up with models in order to be able to do fate and transport and treatment and remediation. I'll mention very quickly, states are pushing forward very quickly on some of this. As a result, some examples, I'll just throw a couple quick slides up. New Hampshire, for example, is going out and doing some inventories across their state, across multiple source types. That information is all out there and available on their websites. The state of Nebraska, I just met with them last week. They are doing an inventory of potential sources. They will then follow that up with some actual sampling to confirm, but this is basically based on industry codes. So here's their particular footprint. And then Florida has also started with some inventories looking at things like AFFF as potential sources. We're actually going to be working with them a little bit on a fire training facility to help them understand sort of the long-term fate and transport, some of the forensics. So the states are going out in front and getting some of this information as the federal response is also coming along. It just keeps moving several at a time. The last thing, I guess, is if we think about it as source waters, it can certainly end up in surface waters, and we have seen that in some instances, but it often ends up in groundwater. And these groundwater plumes can be massive. These are very large plumes. In some cases, for example, in this Minnesota plume, you've got 10 plus miles covering over 100 square miles of area. So it has the potential to impact not only public water supply systems, but also many of the private well systems. And we're seeing this not just in this particular instance, but we're seeing this in a number of cases where once it's in the groundwater, it's very mobile and it's difficult to remove and manage. And so additional work is needed in order to look at treatment technologies for groundwater as well. A little bit about where we're spending our time when it comes to sources and site characterization, a lot on analytical methods going on within ORD, and I think we'll hear some about that here in a little while. And most of these, when I'm speaking analytical methods here, it's targeted methods, so quantitative targeted methods. We are spinning up some work looking at PFAS totals, so in order to get our heads around thousands of chemicals, it may not be important all the time to measure every chemical. It may be that we can get away with looking at something like a total organofluorine as a surrogate or as a screening tool or as a routine monitoring tool and save some of that more expensive chemistry for the times you need to know exactly what's there and when. Non-targeted analysis has come to the forefront. Thank you. Specifically for PFAS, it's been applied in something like Cape Fear. That was an example where non-targeted analysis, they were seeing distinct peaks. They did the work, they did all the and it's hard work, all the forensics that goes into determining what that compound is, and it was determined to be Gen X and some of the associated chemicals. So non-targeted is a very valuable tool. It's one of the tools in the toolbox. It is, however, not a high throughput method and is also very limited commercial availability. However, it is an important tool to consider if you're trying to basically look at what exactly is in your water, what exactly is in your sources, and trying to connect those two. So in conclusion, I think I'm pretty close on time. Many potential sources of PFAS. We need a lot more characterization to put them all in perspective. There's certainly a push to look at a number of these potential sources. What's important, though, is once we get our hands around what these sources are, we need to sort of put them in perspective. Where is the greatest risk coming from? What is making it out into the environment and ultimately impacting human health and the environment? We need information on formulations in both past and current use. There is a large legacy of these compounds that have been used for a very long time in a lot of applications. As I've mentioned over and over, industry's been good about changing these formulations, and so we need to know about what was being used. And a classic example is AFFF, the firefighting foams. Those oftentimes were sold under the same brand name and the same part number, and those formulations changed very routinely. And so it makes it very, very complicated for us to go back and sort of reconstruct that history and figure out what we need to focus on. Management of risk starts with interpreting the exposure pathway. We've got to sort of, the same follow-on comment, we need to understand where those sources are, how they're making it to our endpoints, and then how we can disrupt that pathway. There's been significant investment in research and demonstration projects across the federal, state, and academic private industry side of things, and we're starting to see some impacts of that in the form of analytical methods, understanding some of the toxicity. We have some baseline for a number of treatment technologies. So we're starting to see the payback on that investment. We should see more as time goes on. And I guess with that, I've got 1 minute or less.
Amy, we might have time for one quick question.
Could you speak to the toxicity effects of these endocrine disruptors or carcinogens? What are the toxic effects?
Yeah.
Can you repeat the question?
Yeah, the question was, if I can paraphrase, is what are the toxic effects of these particular compounds? That's a difficult question also outside of my area of expertise. I can say that they appear to be impacting a number of different endpoints. So it's not just a carcinogen, it's not an estrogen disruptor or thyroid disruptor. It's a little bit of all of those, and it is also, we're talking about a very broad category of compounds. It may be even a bit unfortunate that we've called them one thing, because in reality, we're talking about a very diverse group of chemicals, and all of those are going to have potentially different endpoints for toxicity. So it's going to be a little bit challenging. If we just narrowed it down to something like PFOA and PFAS, we could have probably a better discussion about what those endpoints are. But if we think about all the compounds that are out there, it's widely variable. Yeah, thanks.
Thank you. And so we'll be moving on to the next speaker, and up next we have Dr. Steve Wendelken. Dr. Wendelken is currently serving as the Senior Analytical Chemist for the U.S. EPA Technical Support Center. Additionally, he is the Project Officer for the Analytical Laboratory Support, ALS, contract at the EPA in Cincinnati, Ohio. He has over 23 years of method development experience, with the last 18 years being spent at the Office of Groundwater and Drinking Water Laboratory. During this time, he has worked as a senior analytical chemist and principal investigator on multiple EPA drinking water methods. His background encompasses a broad number of analytical techniques, including GC, GCMS, GCAED, LC, LCMS, CE, UV-Vis, SPE, and electrochromatography. All right, with that, we'll turn it over to Steve.
Thank you, Hannah. Good morning. Well, we can thank Mark because we don't have to do PFAS 101. Fortunately, I did not put too many slides like that in there. I've only got just a couple structure slides, but just to show you a little bit about what we're talking about and what we're doing. So first, we have a disclaimer that my opinions are my opinions and not the agency's opinions, and I guess the secretary will disavow any knowledge of my actions. So as I said, we're talking about per and polyfluorinated compounds. Mark's been through these. I think we're all aware of this information, but I'm just going to point to the last two bullets here. And Gen X is really a process. It's not a chemical, but people have kind of taken the name Gen X and put it on the chemical. The process, though, is interesting because of what Mark was saying about what went on in the Cape Fear River down in North Carolina. And so that's kind of critical to the method development we're looking at. And then also PFBS, the second thing that we're looking at is to try and incorporate some of those shorter chain ones that were not incorporated into 537 to begin with. So PFBA was one. We could not do that when Jody did 537. So we were looking to incorporate both of those. So just a little history about how the methods we have evolved. Initially, the first method done was in 2009. That was 537. And that was by our ORD colleague, Jody Shoemaker. And that method was used in UCMR3. They surveyed for 6 compounds, mainly PFAS and PFOA that were the big ones that they were targeting. And we didn't hear a little bit for a while, and then probably very late 2017, 2018, very early, we started to hear the news about what was going on down in North Carolina and Cape Fear. And they came to us and said, hey, there's this Gen X out there, and they're finding other related chemicals like Gen X out there. Can we get a drinking water method for this? And so we took a look at it and started getting a plan together and looking at some of the targets that they identified down there. And we're initially getting ready. Well, we did start on that effort. And in the meantime, about spring of that year, they came and said, we're getting ready to release some health effects data on Gen X, and we'd really like to have a method available for it at the time that information is released. So we talked to Jody, and since we were further back in the timeline of development, we thought about the idea of incorporating Gen X and maybe whatever else would easily drop into 537 and creating 537.1. And so that's essentially what she did. She took the existing method, she took some of the compounds that we had identified, essentially tried them, and if it worked, it was in. If it didn't, it was out. And out of the 10 compounds we gave her, 4 were actually added in 537.1. And then with that done, it was kind of a question, well, one of the original goals of the method we had started, that is the method that's going to become 533. Now that Gen X is already in the other method, how do we deal with that? And so the decision that was made was to continue to keep all of these unique things that were seen in North Carolina and try and add these short chains, and then try and add some of the legacy PFAS compounds in there too, to kind of create one method that had a very broad scope and maybe would apply to a lot more folks. The big changes then that we do have in the 533, there's 11 analytes now that are not in 537. There's an alternate preservation scheme, and we've changed the SPE to weak anion exchange. And then we're also allowing quantitation by ice-step dilution. And you're not expected to read all these, but it just shows roughly what is in each method. And if you just look at the column method 537.1 there, there's 2 of the legacy compounds, C13, C14, and then the net meth phosphate compounds. So other than those 4 compounds, 533 captures everything else that's on the list. So this is structurally what these guys look like. And Gen X is the third one on the top row from the left, HFPODA. So that was the original thing that we were tasked with. And so when we started to build an analyte list, we were looking for things that would be compatible and, you know, retain similarly on a specific phase. And that generally meant that they either had to be charged to the pH we wanted to work at. So we pretty much stuck with either sulfonates or carboxylates so that they would have a fixed charge. And the other thing interesting to look at these, when you looked at the structures that Mark showed, if you notice, there's ether linkages in quite a lot of these. And I don't know, I think that may be by design by some of these manufacturers to promote degradation, that it could be hydrolysis point. So again, to try and get these things from being long chains down to shorter change. So what problems did we face? Well, the first one for any targeted analysis is, unfortunately, you need a standard. And, you know, a lot of these things they identified by non-targeted analysis, so they just worked it up with a lot of homework and mass spec horsepower. And so when we went out looking for standards, we actually found there was 4 of these compounds we could not find or purchase. And in fact, we went to someone that does specifically fluorine chemistry and said, could you make these for us? And they said, hell no, we'll blow the lab up. But I think that's relevant to Mark's point of these things come out of industrial process and may, you know, be formed under conditions that are industrial process conditions. So it really, I think, becomes relevant of it's a very difficult task to predict what's going to be, you know, in the soup with these. We did have 4 others that we wanted to include. We did find technical grade standards for, and obviously there's not isotopically labeled standards for all of these compounds either. So the standard, you know, thing is an issue. I think it's going to continue to be an issue for targeted analysis, although I do hear more and more folks, and I believe even within EPA, are beginning to synthesize some additional compounds in that, so we may have access to some in the future. Another thing was that once we tried to put these disparate things together, we found that a lot of them are susceptible to forming esters. And so you have to control the storage conditions of the standards properly and keep certain ones in a basic solution so they don't esterify. And then probably the worst problem is intermittent background contamination. This stuff is everywhere. We saw some similar actors, or frequent actors, I should say, PFBA being one that we encountered quite frequently, but we started out and it took us a while to just get the instrument clean, get the lab clean, get background down. And, you know, we'd work for a week or 2 and all of a sudden you run a batch and boom, you got a hit and you've got a contaminant there. It's like, we haven't changed anything. We haven't changed lots. We haven't, you know, she's wearing the same clothes she wore last week and it just shows up. And I think it's, you know, going to be a thing for laboratories as these numbers go down and down and down that, you know, I think we're going to hit a point where sometimes we're going to be background limited on what our reporting limits can be just based on the ability to eliminate them from the lab. This is just a list, and again, not to read in detail, but it just illustrates that we've got 16 labeled compounds to use as isotope dilution standards. If you see the ones in green there, those are the ones that we do not have them for, and quite a lot of those were ones that were on that diagram that I showed you that correspond with what they were finding in North Carolina. So we finally got our standards, as many as we could compile, and started to set up. And the chromatographic conditions are actually rather simple. It's just a binary gradient with 20 millimolar ammonium acetate and methanol. and using a C18 end cap column. So there's nothing really special about that. But if we look then what goes into the chromatogram, the first thing is we have 3 internal standards, okay? And those internal standards are not internal standards that we use to quantify the target analytes with. Those internal standards are in there to quantify the recovery of the isotope dilution standards, so we can put quality control around the isotope dilution, so somebody's not getting a 2% recovery and, you know, get out of control real fast, not even realize it. So we've got the internal standards, then we've got the isotope dilution standards, 016s, and then 25 of the target analytes. So 44 compounds in a, you know, 18-minute run roughly. So we're certainly using a fair amount of mass spec horsepower to do this analysis. And this is just an example chromatogram, everything put together all in one place. One thing that I see, and I've even seen this, we're just tying up a second lab, is that the first thing people want to do is they see a 20-minute long run and they go, I can make that 7 minutes, crank that thing up, get this moving, you know. And I get the concept of throughput, and if it's done properly, you know, and you have the right chromatographic equipment and separation, you have the right mass spectrometer, you can do it. But you have to be careful because there's stuff there that you just don't see all the time. And we know the Achilles heel for LC-MS is matrix suppression and enhancement. So this is just a diagram illustrating from one of our high TOC extracts. There's this huge UV background that's there, you know, through almost half the chromatogram. And that certainly is influencing the response and recovery for those targets. And here's just a picture that illustrates that clear. The red line on top had the high TOC, and you see the signal enhancement compared to, you know, reagent water. And so, you know, these isotope dilution standards can help you, and they're great, but they're not miracles either, you know, and there's a lot of things in here that don't have a specific standard. I mean, obviously, we're tying that compound to another standard, but it's not the best because it's not truly identical. So just a user beware message. So we get through chromatography and we're looking for solid phase, solid phase extraction phases. And we settled on a polystyrene divinyl benzene diamino functional SPE. And even though we call it anion exchange, it truly is a mixed mode sorbent, because, you know, you've got the ability for the polymer there to get hydrophobic things sorbed to it. And I mean, you can even get pi-pi interactions out of that benzene ring, probably not with these fluorinated compounds, but with your matrix. So it's possible to pull out stuff that you'd rather not have in your extract. So the final method procedure then, we start with a 250 milliliter sample, which has ammonium acetate in it at the sampling. Add the isotope dilution analogs, extract with the wax SPE, evaporate to dryness, reconstitute in 80-20 methanol water, add internal standards, and then analyze by LC-MS. And then one last additional piece of work, we did actually a couple storage stability studies. This is just a snapshot of one, but this was a finished water that was bacterially seeded and let go for, I believe, even longer than the 28 days. I think they took it out to 35 days. And we really saw nothing except maybe a little bit of loss of those last two compounds. And my guess would be is they're probably sticking to the bottle after sitting there for a while. If they had done an aggressive washing, they may have got those back, but certainly all within quality control limits. So here's just some data. Reagent P&A, that's a 10 nanogram per liter sample. And then if we take it up and do 80, and then a finished groundwater sample. And this one's interesting, is the PFAS right here. Let me try and see if I can make this work. Laser pointer. There we go. So if we look at the PFAS here, the reason that actually is so low is that it's a 10 nanogram spike, but the PFAS concentration in that water was like almost 30 nanograms per liter. So it was a very small spike into a larger amount, and that's why that recovery looks skewed. And then again, finished groundwater at 80 nanograms in surface water. And if you see, some of these things are not consistently bad actors. Some of them tend to be a little bit, like 4,2-telomer sulfonate. We've always had matrix issues with that compound. Even with the correction from the isotopes, we still have had issues, and that's one particular target we've not solved that problem with. But it's interesting, when we did our second lab, majority of people didn't seem to have the same problem. So I think there's a very high instrument component to what performance you'll get. And let me get to the next slide there. There's just an 80. But let's talk about this one for a minute, because what these are LCMRL values. So for anybody that's not familiar, it's a value that we calculate the lowest concentration minimum reporting level. And what it basically says is that the number it gives you at the 99% confidence range will be within your quality controls at your low limit, which in our case would be 50 to 150. That's what's fixed into the calculator that generates these numbers. But it's interesting if we look at net FASA, 3 of the labs had issues, and I spoke to one guy. It didn't perform well on our mass spec. He couldn't even see it. And then there was a third person that it was acting a little funny, and then the other 3, it worked perfectly. So I think there is, a very instrument dependence to some of these particular targets. And it's just a matter, I'm sure, of electrospray, ion lenses, how things are set up, the way voltages are applied. But you do see differences, and I'm certain it's in the instrumentation. But the more important thing here is that when we started, our target LCMRL was 10. And aside from the NFDHA, most everything except for 2 compounds there are under 10. And if you look, a lot of the labs are really under 4. So, we're certainly going to be able to work at limits lower than the previous methods. And I think it's going to depend that the methodology shows the methodology is solid. The multi-lab data shows that. It's just, if you got a better instrument, you can do a better job, is what it comes down to. This is some raw data that's kind of hot off the press. And what this is from our second lab. This is cut out completely just directly from their spreadsheets that the participating labs sent into us. So it's a variety of levels. It's a variety of matrices. I know we've got groundwaters, we've got surface waters, others in there. And The red lines would be the 70 to 130 QC limits that we would have for anything that's not 2 times the MRL. And all of the data is really looking good from the second lab. So we're hoping to do a final review within a week here and compile the comments from the second laboratories. I'm expecting that once that's done, it will go into formal review for publication number, and we're hoping to get it posted by the end of October, if we can. So it should be up and ready for use. So in conclusion, PFAS method development is a high priority at EPA. There's quite a lot of folks working. The isotope dilution in this, I think, has really increased the robustness. The lower reporting limits, as we saw, will certainly compare to 537. Method development and other work on PFAS, there's certainly other groups and other parts of the agency working on this. We've possibly discussed taking it, and we normally don't expand to other matrices because we're specifically drinking water, but we've been thinking about taking it because the agency had some needs, maybe into surface water, maybe into non-potable groundwaters, things like that, and do an evaluation there. And then what was, oh, the last bullet there, they're considering proposing PFAS for UCR5. Honestly, off the top of my head, I don't know what the deadline is that they have to make that final cut and decision, but I'm certain if anybody's interested and they go to Google EPA UCMR5, it'll pop up and get them to the page where there's information about what targets they're looking at, where they are in the decision process. And with that, I will be glad to take any questions if we have a few minutes.
Yeah, we've got about 5 minutes.
Hi, thanks, Steve. I had 2 quick questions. One was for your second lab comparison study, did you tighten down the instrument variability in the method? Is that how you got the improved performance on recovery? And then as a follow-up, are you guys considering any type of total fluorine method?
For the first one, no, there was no specification for their instrumentation. It was just some labs had better instruments than others. So we didn't, change anything specifically. They just, everybody took the method, it ran it as written, and those are the results. And then regarding total PFAS, that's kind of the holy grail, I think. And we're certainly thinking about it. Everyone's thinking a lot about it. It doesn't look, in my estimation, my personal estimation, that any one of the technologies that are out there, market mentioned, are really like coming to the top is, this is going to be it. It seems like there's a variety of, well, you can get this total or that total or this kind of, it's to really do that, I think is going to be a difficult task, but I can guarantee you people are thinking about it and working on it.
Hi, Steve. So thinking back to the slide where you had the different compounds with the different functional groups on them, and I just wanted to check and see if I heard you correctly that were some of those compounds engineered to promote, or those functional groups put on to promote degradation of the compounds, is that correct?
I don't know that the functional groups are. My speculation is that the ether linkages, okay, so where you've got that oxygen in there, that could be a point of attack for a hydrolytic process or something like that to allow, because if you got that straight fluorine chain, that's what's so stable. It just won't go anywhere. And my suspicion is by breaking that up, by putting that oxygen in there, that it may help. Have I seen any degradation studies or anything on these particular compounds that would indicate that's true? No.
Okay, thank you.
Hi, sir. My name is Mike Eller. I am out of EPA Region 3, a leader for a enforcement division sampling team. We've been asked to go out recently and sample some non-drinking water matrices for PFAS compounds using method 537. So 2 questions for you. One, there's some indication in the very little bit of literature that I've read that there are certain PFAS compounds that partition and sorb to suspended solids in source water. I'm wondering what, if any, work is being done to work on a method for PFAS in solids. And the second question is there any way to source track this stuff, whether through stable isotope, mass spectrometry, or something else? Thanks.
I don't, honestly, that's a tough, I mean, the soil issue, I can say I know there are people working on that. I don't have direct contact with it being water. And the other things too, biota, fish tissues, all of those kind of things. I mean, Mark, would you want to add anything on that?
Yeah, EPA is working on methods beyond drinking water. There is a direct injection method that is just closed for comment, that is available for non-drinking water aqueous samples. For the solids, we're working with a number of partners, including DoD, to accelerate the methods development effort. It will likely go through both Clean Water Act and SW 846. So there'll be 2 options for those solids methods as those come along. We're probably looking at something in the 12-month time frame at the earliest that those get out and promulgated. And what was the last one?
About isotopically tracking these things.
Yeah.
I have not.
Yeah, as far as I know, not isotopically. There are efforts to look at forensics. As I mentioned when I was speaking, it is complicated because the formulations have changed over time, even if they're called the same product. So it's going to be a challenge, but there is work going on. I know DoD just released a series of projects. I'm on one of them that is going to specifically look at whether you can develop those profiles that would say it's coming from a particular sector, like an industry or application sector, but how those all get mixed together in an environmental mixture is going to be a challenge.
Couple questions from the webinar series, so I'm going to combine them. So what's the definition of your finished drinking water, and also have you seen any kind of impact on TOC on the recovery of these contaminants?
Well, to the first question, finished drinking water just being what would be supplied by a plant to entry point in the distribution. No, I mean, we do measure characteristics when we do these. So like we will get TOC measurements on them. We will take hardness measurements and that when we use those for, the data and the method. But there's not one specific thing that we target. It's just a matter of we go take water from that source, measure those things that we can, and record them just for posterity. Well, yeah, there is. In fact, that slide I showed where you saw the signal enhancement and you saw the TOC background in the chromatogram. Yes, there's definitely an impact in TOC, and that's one of the reasons that, it's nice to turn up the flame and get things done, but you got to remember sometimes it's not just separating those targets from one another; it's separating the targets from background contaminants that cause problems.
So our next speaker is Jonathan Burkhart, is an environmental engineer with the US EPA's National Risk Management Research Laboratory, NERML, and the Water System Division. His research focus areas include water treatment modeling, distribution system modeling, premise plumbing water quality modeling, and event detection technologies. He has worked in these areas since 2013. Dr. Burkhart received his PhD, MS, and BS in chemical engineering from the University of Cincinnati.
Thank you. Today, I can acknowledge the co-authors here, but also there's about 6 to 12 people in the room that can also answer a lot of the questions. This is going to be really high level sort of airplane mode view of what we're doing from the drinking water side and some other resources to find out, where you can find more information later on, and just as we get more information, we'll put it there. So again, acknowledge the disclaimer. My opinions are his opinions. No, that's not how that works, but I'll just skip to this slide. The take-home message from this slide is just that it's complicated. I mean, both the previous speakers really highlighted the fact that there's a lot of different chemicals, and from the treatment side, that can lead to complications because some of them stick better to certain adsorbents or move differently in the different technologies, and so that's really important to sort of understand, and we're trying to get a good view of a lot of these technologies. As we're getting analytical capabilities, we're able to get better low end understanding of the non-detect and where that is, but also just being able to keep track of what these chemicals do in the adsorbents. And so this is a really broad overview of what we're doing, and we're bringing in a lot of research, performance research. We're also working with the Office of Water for costing research so that they can understand how these technologies are going to impact utilities of a variety of different sizes, and I'll talk a little bit more about that later. We're putting a lot of this in the treatability database. I'll provide a snapshot of what that looks like, and as we get more information, that's going to be put into the treatability database as well. We're doing in-house research on actually the treatment technologies. We just put out a paper, Craig's in the audience, for the point of use, point of entry for the GAC and RO, and is currently going to be starting some work for ion exchange for point of use, point of entry as well. But we're trying to also bring in performance modeling, so performance data, but then being able to model that to full scale work as well. So I figured I'd start with the things that most of you probably care about, and that's the effective technologies. So if I lose you, at least you heard this part. Most of the conventional technologies to date are really ineffective. The low pressure membranes, biological treatment, and so on. But there are a few technologies that have shown promise for removing PFAS to some degree. The anion exchange resin, the high pressure membrane or RO, and the granular activated carbon, specifically when it's designed for PFAS removal. Powder activated carbon at high doses has shown some effectiveness, and so that may not be very effective for long-term treatment, but again, it may be if you have a short-term plume that you're trying to treat, it may be effective. So the big picture, people want to know what the advantages of these technologies are. GAC has been the most studied technology, and so there's a decent amount of data for that. It will remove 100% of contaminants for a time, and that's the really important part. It's the for a time, so it's designing to treat to the goal that you're hoping to achieve. It has a good capacity for some PFASs, and it will also remove a significant number of the DBP precursors. It will also remove many of the co-contaminants, and it will likely help to maintain disinfectant residuals, and it may also have a positive impact on your corrosion control. Anion exchange has similar removal for a time. It will remove 100% for a time, and it also has a high capacity for many PFASs. It has a smaller bed for than relative to GC, which could be of use for some especially small utilities, and it will also remove co-contaminants. High pressure membranes are a different type of technology. They're just a size exclusion technology, but they have a high rejection rate for PFAS. They will also remove many co-contaminants, and they will also remove the disinfectant byproduct precursors and helping to maintain disinfectant residuals.
Is that a single pass ions changeover?
Yeah. And so, you know, you have to take the bad with the good. So the issues to consider with these technologies is that the runtime for shorter chains, if you're concerned with shorter chains, is low, so that they tend to break through very quickly relative to the C8 length PFASs. They can potentially overshoot if the design, the bed design is not appropriately sized, and so that will actually release more PFAS for a time. What you do with the reactivation and removal, how often do you have to reactivate that, and what do you do with that material? So ion exchange also has a similar challenge with shorter chains. They tend to be, they move through the column quicker, and they can also overshoot if the column's not designed appropriately. It's unclear with maybe secondary benefits that you can get. And again, you have the disposal of resin. So what is that going to happen? For the RO technologies, those tend to be more expensive, and so that can be a challenge. They have to be clean because they continue to foul. So again, depending on how the propensity for your water to foul those membranes, they would have to be remineralized, which was discussed in the earlier talk, and to deal with corrosion control. So they tend to make the water very corrosive if you don't post-treat that water. And then what do you do with the concentrated stream? Can you dump that to your waste treatment facility, or do you have to further treat that before putting it back to your waste treatment? So the goals of the research are just to try to give you as much information so that you can make the best decision that you can, to understand how you can make a reliable, robust system to deliver water to the customers. And then again, that includes a variety of issues: capital costs, long-term maintenance, what training or what staffing issues. Are you going to have the staff that can keep up with the new technologies, and what are the various reliability issues that you might have to be dealing with. And a big thing is also just avoiding any unintended consequences. Again, this was also mentioned earlier today, but you don't want to have a technology that's going to change something about your system that then will cause a different issue unrelated to PFAS. And so we're trying to provide as much information about that as possible, so that utilities and regulators can make the best decisions for these technologies. And so the goal is, again, to achieve as many positive benefits. Many of these technologies, as was mentioned, will also produce improvements in residual maintenance or DBP reduction in your system, and so that can be a good thing for this system. And so I'm not going to talk about specifically the research here, but just where you can find out more about the research. And so the EPA actually has a treatability database where they are, we have been putting information about the various treatment technologies, different compounds, and you see here we've got a list of, this is actually a snippet of what's available currently for PFAS, but also nitrates, perchlorates, and microcystins. And if you search EPA TDB, that should take you there. There's a link at the last slide as well. And so this is maybe kind of visible, but basically this is what the current version of the treatability database looks like. And so the circles there highlight a couple locations where you can go, and it's actually circling find a contaminant and find a treatment process. So it may be a little hard to read there, but it's easy to navigate. And so if you actually go to the per and polyfluoroalkyl substance page, you see a list there. I don't expect you to be able to read that, but those are the compounds that we have any data available for now. And in the, how do we actually get to that? Oh yeah. And so if you can see the pointer there, maybe it's hard, but the top there is overview. You can drill down and look at the treatment processes that the data is available for, and then references and fate and transport and properties of those compounds as well. So it's a good place to find some data about these different compounds, you know, outside of these talks. And so, you know, one of the big challenges is we want to be able to, you know, have more and more data, and so we're collecting that data from more sources, including internally generating that data about influent concentrations, because that's going to directly relate to how your system is going to perform. Other competing contaminants that are associated specifically for ion exchange, those can be important for how they relate to PFAS. Other influent characteristics, TOC specifically, and then certainly, you know, collecting data about RSSCTs, pilot scale, full scale. I mean, the bigger the scale, the better the data in some ways, because you can get a longer picture of what's happening in the system. But mostly the data is RSSCT or pilot scale. Obviously, the type of material that's used as an adsorbent is important. And then, you know, one of the big challenges when looking at literature or, you know, understanding this is, you know, what does breakthrough mean? Some systems only look at the first point beyond non-detect. You know, we had a good talk about what, you know, what the detection limits are. But if that's your breakthrough point, that may only be, you know, a little helpful. Or are you going to a target here? You know, a lot of utilities are using 70 ppt, the health advisory for the PFAS and PFOA, or is it just a % breakthrough? And so understanding what that breakthrough number is important. And then obviously raw data is the most important, because then you can really drill down into what that means for the technology. So one of the specific things that we're doing is looking at modeling to extend the usefulness of RSSCT or pilot data or full-scale data to different scenarios. And in this, you know, figure here, we have, you know, an influent. Just this happens to be PFBS, but that's in orange. The blue is the pilot data that was the effluent, and then the green line, the solid line there, is the modeled prediction for what that looks like. And once you have those parameters, you can extrapolate that to a full-scale scenario and then ask different questions. And so you can, you know, make the pilot data a little bit, you know, more valuable. And it's not, you can change things like empty bed contact time, or looking at different size of system, or number of contactors, or a variety of questions that would be relevant for utilities or regulators. And this is a slightly different picture. Again, just more modeling results. You know, the take home here is just, if you look at this top figure, that happens to be PFOA. Based on the influent concentration, this predicted breakthrough is almost complete at, you know, about 1,200 days, whereas the PFAS is, you know, predicted to be a little bit more of a sharp transition, but that's only actually about 25% broken through. But again, once you take that, you can see that that line is predicted beyond what the data would provide. And so you can actually predict to like the full scale or full breakthrough if that's relevant to your objectives. And so we're trying to, you know, bring those tools. As Tom mentioned, we're going to, you know, be sharing the models that will, you know, freely, so that people can run the models themselves. So a slightly different perspective on this is, you know, looking at design evaluation. And so these are two different concentrations. The one on the right is a higher concentration. And you can see that for the variety of PFASs, the actual treatment throughput, which is what is on the y-axis, is sharply declining at higher concentrations, which sort of suggests that you want longer empty bed contact times for PFAS removal. And that's sort of consistent with what a variety of sources has shown. And so now I'll sort of transition to some other research, which is more on the costing side, and look at some work that's being done to understand, and help predict what the cost of treatment is. And so that method is the work breakdown structure approach. You may have seen other talks on that as well. I think there was one on the webinar series not that long ago. But basically what that does is, we take all of the different components, the vessels, the valves, the instrumentation, make predictions about the size of the structure that would be needed for that type of approach. And we actually have a cost that are, routinely updated to give a prediction. If a plant is a certain size and it has a certain throughput, what would that look like on the costing side? And that helps from the regulatory side to help understand the cost of regulating. And so the costs are actually broken down into capital costs, which are going to be your investment cost, the cost of pumps and so forth. And then pilot studies and permitting would be included in that, because that would be more of a one-time cost. But then it's also tracking the annualized costs, so cost of labor, cost of chemicals, cost of maintenance and pump replacement and so forth, and even down to how much energy it might cost to run a pump. So the cost model is actually specifically for PFAS. We have data for anion exchange, GAC, the point of use, point of entry, and RO. And so it's a pretty good snapshot of what those might cost. And I have a few slides on just highlighting that in a second. But if you look at the bottom there, we can search for EPA WBS, which is the work breakdown structure, or there's the link as well, which you should be able to download these slides. So if we look at just some approximate costs based on different data that was already collected, we can see that the blue line here in the middle, which I'll try to get evidently, so the green is trichloroethane, so TCE. The PFOA, which is approximately breaking through at about 70,000 bed volumes for this specific example, or the 1,1-dichloroethane. So you get some, you see a snapshot of what those look like in terms of cost. And this is, you see these three distinct sort of shapes to the curve, and that's the smaller systems, medium-sized systems, and large systems. So the costing is actually broken down into those three sizes based on the average flow that would be expected. And we see that the weaker adsorbing compounds would have a higher cost if that's your treatment goal, and that might be to be expected. So if we actually look at specifically what the total annualized cost for the variety of compounds would be, the lowest line there is the PFOA, and that's the green. And then the other two lines are almost identical, and that's the Gen X. So if we treat for a Gen X removal or 1,1-dichloroethane, those are both more weakly adsorbing, and so the costs would go up. And again, you see the sort of the breaking in the line prediction because of the size of the system. And again, we would have compounds would have a range of costs depending on the water quality or other factors, and we can take that into account to some degree with this approach. And then we found that the smaller systems under 1 MGD can have a cost savings for a variety of reasons. They might not need booster pumps. The structure might be smaller. They might not need the same thickness of concrete pad because the overall weight of water or whatever is lower. And then they might have reduced indirect costs and a variety of things that a larger system might have to deal with. And so in terms of validating this, we're pulling in as much data as we can with different partners, collecting data from even sources like the DoD as it's available for as-built cost installed. The more discretization in the data that we can get, if we have a full line item quote or as built, that's great. But then there is the bullet. If we just have a total only, at least it sort of gives a point to say, well, this is in the right ballpark, and these are all continually reviewed by experts in the field as changes are made. But then it also looks at different material costs, so stainless steel versus plastic, and you can make different decisions in that. So I will leave this slide up. This is sort of the concluding slide, but these are some resources that are available right now. The website that's up there is the data and tool website that sort of compiles a variety of the resources for the PFAS. And then you can actually get to the treatability database and some other information from that page, or the bottom link is actually the treatability database directly, if that's of interest. And again, that has a lot of different data and a compilation in a way that hopefully is useful to utilities. And at this point, I can take any questions.
Cindy Clevens from New Hampshire. To ask if you have, if you could share some data about the different carbon types. I know there's a difference in treatment between the bituminous carbon and the coconut-based carbon. Can you expand on that?
Yeah, so the question was just to provide some more information about the different types of carbons. And that's something that's ongoing. We're definitely looking at the different carbons, and there is a little bit of a difference in terms of treatability with the different carbons. But so we have some pilot data that's pretty comprehensive, for a surface water. But in terms of specifics, I think it would really depend on the utility, the water that they're actually dealing with. So yes, technically there's a little bit of a difference in some cases for some compounds. One might be better than another, but sort of across a sweeping compound or a sweeping statement, about is one better or worse for PFAS is maybe a little premature, and so that's work that we plan to do. So.
Hi, my question is, the powder activated carbon on the slide, it says it's effective in some applications. Could you just explain that a little bit more compared to the GAC?
I'm sorry, could you repeat that?
The powder activated carbon,
yeah,
it says it's effective in only select applications.
It's more of just the dosing required. So it's over, I think, what was it, 50 milligrams per liter or whatever. Dosing, and so it can be effective at higher concentrations, but it sort of becomes ineffective below some sort of critical dosing. So it's similar technology, but it's just in the powdered application, the contact space is less, right? So it's not flowing through it in the same way. So. Yeah, it's not going to be as good, relative to a GAC type application, but it could be for specific situations. It might be it could be effective.
All right, thank you.
Yeah.
So you mentioned that, speaking to the end fates of some of these treatment technologies, you mentioned that reactivation is one way to deal with GAC that is used to treat for these compounds. Did you come across any studies or tests that looked at the effectiveness of reactivation at eliminating the perfluorooctanated compounds out of GAC?
So I don't have that specifically, but that is something that we are interested in doing, internally, and hope to do to understand that. Is it effective at removing it in the reactivation process, and also then what's the fate in the reactivation process as well?
Okay.
Yeah. So.
Going back to your slide and comparing the GAC and ion exchange, I believe you said that there were short run times for each one of those. And I wondered, do you mean by that there's a short time between time of startup and the time they get saturated? And if so, what do you mean by short?
Well, that's going to really depend on how much is in your influence. So the question was just, what do you mean by short in terms of short runtime? And that was specifically for like the short chains. The short chains can be, a period earlier, but it really is going to depend on the sort of complex interplay between, what compound we're talking about and the carbon. So again, it's sort of a longer answer, but it's in the, months, 30 days maybe versus 90 for some of the longer chain compounds. But again, that's going to be really dependent on what's on the influence side. But it could be significant in some cases, especially if the utility is particularly impacted by the shorter chains.
Thank you.
So, but again, we can have a conversation offline.
Right. Is there time for one more?
Oh, sure, yeah.
Thanks. Sorry, given the lack of standards, I was just curious how you were developing your bench scale studies and what you were using as your source material, and then the analytical methods that were used in those as well. Thanks.
Yeah, so from the bench scale, we're looking at, different occurrence data. So that's part of it. For the point of use, point of entry study specifically, we looked at max day concentrations in an aquifer that might be expected. But, we're looking at the whole breakthrough curve. And so especially in the modeling that we showed, or I showed, that model's developed obviously under some set of circumstances, carbon and influent concentrations. And then we can use that to inform if a regulation were to come down or something along those lines. We can use that data to inform a process after the fact. In terms of the methods, I think you asked about, we're using either data from sources that might be a commercial lab or internal data that would be collected under the standard methods that would be available for these technologies, so, or the compounds. So.
Thanks.
All right, well, thank you everyone for attending this session. I think with that, we'll go ahead and wrap up.